Okay, so what I would like to mention here is to give some connections between three concepts, three subjects: graph, algebra, and probability. You know, we have different topics in different subjects. So I am going to give just one of connections between these three subjects. All right. So I will introduce something in three parts and then give some relations between them. All right. So now first of all, let me just give a few remarks on just classification of mathematical sciences. Of course, it's the old classification because the new classification comes from the American mathematical classification, and we have many topics, many codes, and so this is the old classification of mathematical sciences, which of course we use in our universities. You know, I just divided mathematical sciences in three main subjects. So, you know, in our university, we have three departments: applied mathematics department, pure mathematics, and statistics. So we divided in three parts, right? So in each part, for example, in applied mathematics, you can see that we have some sub-branches of applied mathematics. For instance, numerical analysis, differential equations, dynamical systems, operation research, control and optimization, and graph theory, and discrete mathematics, and so on, right? And in pure mathematics, we also have algebra, analysis, geometry, topology, and something else. And in statistics, we have descriptive statistics, we have source of data, sampling concept, regression, data science, probability, and so on. Now, what I'm going to just display here is I want to take graph from the applied mathematics subject, and algebra from pure mathematics, and probability from statistics, right? So I'm going to give these three different subjects from different just fields to combine all together and give some new ideas about relations between three concepts. Now, let us start with the first one. The first one is graph. So I'm going to say something about the graph. Graph is the first one, right? So in graph theory, we know that in graph we have some nodes as a vertex set, vertices, and some line between nodes that we can say edge between these vertices. So as an example, if you take this graph consists of 5 vertices. So I just gave the name 1, 2, 3, 4, and 5, right? So we have 5 vertices, and we have 1, 2, 3, 4, 5, and 6 edges. So we have an edge between two vertices 1 and 3, 1 and 2, 1 and 4, 3 and 4, 4 and 5, and 2 and 5, right? Sometimes the graph may be directed, so we may have edge from 1 to 2, not conversely from 2 to 1. So if we have a direction, that's a directed graph. So we have edge from 1 to 2, from 4 to 2, and from 3 to 4, and also 2 to 3. So if we have no direction, so we can denote any edge by a set of two vertices is 1, 2. This set, because we don't have any order between 1 and 2, and that's because of we don't have any direction, so we can denote edge in undirected graph by a set of two elements, two vertices, 1 and 2. But here, because the graph is directed, so we can display edge between 1 and 2, or exactly from 1 to 2 by order pair 1 and 2, right? Sometimes we may have a loop. Loop means that one vertex can goes to itself. So we have an edge from vertex 1 to 1. And sometimes we may have more than one edge between two vertices. For example, here, if we have a directed graph, so we may have edge from 2 to 3 and also 3 to 4, right? So if we don't have any loop and any just multiple edges, then this graph is simple graph. So we are interested to just give to consider the simple graph, but because it's much easier for simple graph. So in all parts of my talk, I will consider all graphs are simple. So there are some main concept in graph theory. For example, we have connected graph. Connected graph means that we have a path between any two arbitrary vertices. If we have this situation, then we have connected graph. And also we may define the distance between two vertices. The distance is the length of shortest path between x and y. We have diameter is the maximum distance of any two vertices, and also girth is the length of shortest cycle, of course, if we have a cycle. We have some known graphs, complete graphs means that we have, if n is 1, we have one vertex, so we don't have any edge. If n is 2, we have two vertices and one edge between them. For n is 3, we have a triangle. We have 3 vertices, and between any of these two vertices, we have an edge. And similarly for k4, we have 4 vertices and 6 edges, and k1, and so on. We also have complete bipartite graph. Complete bipartite graph KNM means that we have two parts for vertices. The first part consists on n vertices, and the second part includes m vertices. We don't have any edge between any two vertices in the first part, and also similarly for the second part we don't have any edge, but between these two sets we have an edge. Every vertex from the first part will adjacent to any vertices in the second part. So there are some known complete bipartite graph. For example, here we have K3. 4 means that we have 3 vertices from the first part and 4 vertices in the second part, right? And we have an edge between any of these 3 vertices and these 4 vertices. So this is a very short description on graph theory. Now, let me move to the second subject, algebra. So, you know, algebra, when we are talking about algebra, algebra means we may talk about the group. Algebra consists of ring, module, semi-group, semi-ring, fields, integral domain, division ring, vector space, and so on. So that's all concepts in algebra, right? So what I would like to just mention here is to consider the first one is group. So I want to take group from algebra, right? And then give a relation between group and graph and probability. You know the definition of group, so everybody know when we are talking about the group means that we have a non-empty set and we have a binary operation and we have some more properties with the non-empty set, for example G, and binary operation if we denote it by a star. If we have associativity between any tree of elements in G, then we will have semi-group, and if we have identity elements, then we will have the monoid, and if we have identity, if every elements of G is invertible, then we can say that the binary operation G and S star is a group. Okay, now we may have just one more properties. So this is properties for the group. If we have another properties, for example, if for any two elements A and B, if we have a commutative between these two arbitrary elements, then we can say that the group is abelian. All right. Here are some examples, right? So if you take the integer numbers with usual the summation, so it's a abelian group. If we consider natural number is semi-group, but is not group because it doesn't have identity elements, and also even there is no if you take, for example, integer natural number 2, so the inverse is -2 and is not in the natural number. And also we may consider all integers in modulo n, right? And also I'm going to define 3 important groups which we use just several times here in the case of probability and just the graph, right? So we have symmetric group S3. Symmetric group means that if we consider set of 3 elements, 3 letters, we can denote by 1, 2, and 3. So consider all 1-to-1 functions from 1, 2, 3 to 1, 2, 3, right? So we will have 6 functions. So you can see that the first one is the identity function, which 1 goes to 1, 2 to 2, and 3 to 3. And the second function is that we make just take 1 to 2, 2 to 1, and 3 to 3. And similarly, we have the third one is 1 goes to 3, 2 to 2, 3 to 1, 1 to 1, 2 to 3, 3 to 2, and 2 more functions are 1 to 2, 2 to 3, 3 to 1, and 1 to 3, 2 to 1, 3 to 2. So we can denote this these 6 functions just for shorten to this notations. So f1 is the identity, f2 we had 1 goes to 2, 2 to 1, so we can denote it by this cycle, and f3 is 1 2 3 3 2 1 again is the cycle, and similarly f4 is 2 3, f5 is 1 2 3, and f6 is 1 3 2. So the symmetric group consists of these 6 elements. So you can see that if we multiply 1 to so can you hear me? Is that okay? I don't know what happened. Just for a few seconds we lose the connection. such a way in such a way that I times to j is k, j times to k is I, and k times to I is j, and also I square is equal to j square and k square, all are -1. So quaternion group is a group of order 8, and the center consists of two elements, 1 and -1. Okay, now let me move to the probability. So the third part, the third main subject, the probability. You know, the definition of probability is that we can divide the number of ways it can be happen to the total number of outcomes. So if we take A as an event, so the probability for having an event A is the number of ways A can be happen to the total cases for A. For example, if you take a dice here, right, so you can see that if the event A is having number 1, so the probability is 1/6, because we have one case for 1 and total cases is 6. And similarly for event B having numbers 2 or 5, we have 2/6, and if the event C is having an odd number, we have 3 possibilities, 1, 3, and 5, so it's 3/6. Now I'm going to give just the connection between these 3 subjects. The first one is the connection between group and probability. So what's the connection between group and probability? I would like to define a probability in a group. So we can give the name commutativity degree. So the commutativity degree of a group we can denote by D of G is the number of pairs X and Y such that X and Y are commute divided by order of G square. Now we have some examples. For example, if the group G is abelian, so the commutativity degree is 1. For the symmetric group, if we count the number of pairs X and Y such that X and Y commute, you can see that we have 18 pairs, order pairs. For example, we have 6 pairs for identity, because identity can commute with all other 6 vertices, 6 elements, and 1, 2 can only commute with identity and itself. So the total number of pairs is 18. So 18 divided by the order of S3 square is 36, is 1/2. And similarly for dihedral group, we can compute the commutativity degree is 5/8. There are some more results about the commutativity degree. For example, if G is abelian, then the commutativity degree is 1, and conversely, if the commutativity degree is 1, then G is abelian. If G is a finite non-abelian group, then we can just show that there is an upper bound 5/8 for the commutativity degree. We can compare commutativity degree of a group with a subgroup. So the commutativity degree of subgroup is bigger than what we call the commutativity degree of group G. And also if G is a finite non-abelian group and P is the smallest prime number dividing the order of G, then the commutativity degree is less than or equal to P squared plus P minus 1 over P cube. And here is a conditions, necessary and sufficient condition for the commutativity degree to be 5/8. And it's very interesting to see that if the commutativity degree is bigger than half, then G is nilpotent. So now let me just give a connection between group and graph. So I gave a connection between group and probability. Now here is a group and graph. So I'm going to define the commuting graph of a group, a graph related to a group. So if G is a group, we can denote a graph, we can denote it by gamma G. The vertex set is the whole elements of G, and if we take two elements, two vertices, x and y, we can say that x is adjacent to y if x and y are commute. So here you can see is a street. We have 6 vertices, right? And identity, because I know we have h between identity and other vertices, other elements, because identity commute with 1 2, with 1 3, 2 3, 1 2 3, and also we know that 1 2 3 and 1 3 2 are commute, so we will have an h here. And similarly for dihedral group of order 8, this is the commuting graph, and this is for the quaternion. For the quaternion group, this is the graph. Now the second graph is non-commuting graph. Non-commuting graph is a graph related to group G. The vertex set is all non-central elements. So the vertex set is G minus the center of G, right? And two elements, x and y, we will say that x is adjacent to y if x and y are not commute. So again, here is a non-commuting graph for the symmetric group S3, know I don't know what's the problem here. So I just give a connection between the probability and non-commuting graph here, right? So let me continue. So as I mentioned, if we have the commutativity degree, we can find the number of edges here. For S3, we know that the commutativity degree of S3 is 1/2. So the number of edges here, you can see we have 9 edges. And similarly, for dihedral group, we know that we have 12 edges, and here by this relation we can find the commutativity degree. So here are some results between group, graph, and probability, right? So if G is a finite non-abelian group, so the number of edges is bigger than or equal to 3/16 order of G square, right? And here is the lower bound for the number of edges, right? And here is a lower bound for the commutativity degree. So we remove the proof. And here are some examples, some results about the non-commuting graph. For example, the non-commuting graph has no isolated vertex, is connected, diameter is 2, Gersh is 3, is Hamiltonian, is planar, if and only if we have 3 cases. And here are some problems. The first one is to compare the isomorphism between 2 graphs and the order of 2 groups, right? And that's the connection between the equality of commutativity degree and the isomorphism between 2 graphs. And here is the just determining non-commuting graph for dihedral group, symmetric group, alternating group, and generalized quaternion group. Right? And here in the last my page is to give some more probabilities. Here I just defined the probability commutativity degree. We can define the relative commutativity degree, conjugate degree, normality degree, cyclicity degree, and permutability degree. Okay, so I'm sorry that for this unexpected happening. So I will send the link, just recorded link, for all other participants who are not able to attend here. If you have a question, Doctor, I'm just listening your question. Do you have any question, Dr. Kian? No question? Okay. Thank you very much, and hope that in the next time we could able to connect easily. So thank you very much indeed. Bye then.